Hi, my topic is performance analysis of classification using linear analysis and the lofty filter. In fact, I'm going to examine this in the following order. This is the whole structure of my presentation. My presentation will include introduction, theoretical background, experimental results, and the conclusion. So let's start from introduction. With the advances in computer power, there is a growth of video records as an important computer for an application. Content-based images have been an active and fast-advancing research area since 1999. In the CBIR system, images are represented by high-dimensional version perceptive feature vectors. However, the difficulty to index high-dimensional vectors and the gap between low-level vision features and high-level concepts make it ineffective to achieve good performance. In my project, our goal is to create algorithm that trains the computer to extract these distinctive features and correctly classify animals, namely cats and dogs. So let's look at the theoretical background. The first part of the background is principal component analysis. We transform each 64 times 64 grayscale images into a 4096 times 1 column vector. We employ the well-researched theory of singular value decomposition. Recall that for any real value matrix, there exists two matrices and a matrix with entries sigma 1 larger than sigma 2 larger than sigma 3 larger than 0. The typical way of selecting the principal component is by calculating the cumulative energy of the singular value using this formula. We then have the matrix given by this formula. PCA makes a great process to simplify data sets prior to performing intense calculations. The second part of theoretical background is filter banks. The filter mask algorithm is very simple. Again, its purpose is to transform the intensity of each pixel in the image to either 0 or 1. The general procedure is described below here. And the third part of the theoretical background is linear discriminant analysis. The objective of LDA is to find an direction W such that the projections of the data points are grouped with their pace and are separated from strangers. We want data points from the same classes to be close together, and data points from different classes to be far apart. It can be shown that the maximum W that satisfies JW is found by solving this, this problem. Next, we describe that classification process that uses the projection vector W. We use the average of the projected class Y means M1 and M2 to establish a boundary value on the number line that separates the domains of each set. Finally, we project each test image onto the number line and determine which domain it resides in relative to the boundary value. The final part of the theoretical background is novelty filter. The novelty filter algorithm relies primarily on the theory of projection matrices. Projection matrices are important to us because we can decompose a space W into subspaces. Therefore, any vector in that space can be written as a sum of vectors from each subspace. The novelty filter uses this idea to separate million patterns in test data from new or lower patterns. Then let's run the program of this program. This is the experimental results of my project. The red marks represent the dog date and the blue marks represent the cat date. Figure 1 also shows how the test set are classified. After running the classification methods, our results are fairly good. The confusion matrix in Figure 2 shows the results of the LDA classification. Cats are correctly identified more than the dogs. As you can see, 6 dogs were correctly classified as dogs, but 6 dogs are considered as cats. On the other hand, 8 cats are correctly classified and 4 cats are mistaken for dog. In summary, 14 out of 24 are correctly classified, yielding a 58.3% accuracy for the LDA method. Figure 3 shows the images of cats and dogs that were misclassified using the LDA algorithm. The reason why the LDA classifier is not able to correctly classify the particular image may be related to the noise in the background. The novelty filter algorithm performed much better than LDA. In Figure 4, the confusion matrix shows that all cats are correctly classified and only 4 dogs are mistaken for cats. A total of 20 out of 24 images are correctly classified, yielding an 83.3% accuracy for the novelty filter method. And this is the figure of misclassified image using novelty filter. Finally, let's look at the conclusion. In summary, creating a classifier to identify images of cats and dogs can be done with good accuracy. It seems that the simpler algorithm performs better than the more complex algorithm. Using less information seems to get better results. but obtaining more information seems to confuse the algorithm. Applying the filter mask to set the image pixels to 0 or 1s made the image simpler and the shape more discernible. This was a very simple transformation of the image, yet results in high classification rates. Even though the lofty filter gives us highest accuracy, there could be some modification done to improve the classification even even further. One idea is to use the filter mask after applying the median filter or the average filter to smooth out the images. This could be reduce the background noise and make the features more distinctive, possible giving higher rates. This is the end. Thank you so much.